Happy Saturday, scientists! Let's review. This week it's a wonderful world of elements, compounds, and mixtures as we embark upon C2, the second topic for Paper 1 in chemistry. In C1, we learned that the elements were made of three main parts: protons, neutrons, and electrons, and that the protons and neutrons were the only parts with significant mass. We also learned about isotopes, which were versions of the same element that had a different mass because they had a different number of neutrons. Today we're going to figure out how those protons and electrons get to be the mass of the atom and how it all fits together. We begin with the relative atomic mass. The relative atomic mass is one of those terms that we can analyze in order to figure out what it means. Relative means that there's going to be a comparison. Atomic tells you it's going to be to do with atoms, and the mass tells you it's going to be to do with their mass. In this case, what it is that every proton or neutron has had its mass set relatively, and it's relative to 1/12 of the isotope carbon-12. We know carbon-12 would have had 6 protons and 6 neutrons, or 12 things. By dividing the mass of carbon-12 by 12, we're able to set the mass of 1 proton or 1 neutron. When you're looking at a periodic table, the relative atomic mass is what you'll see. Do make sure that you take a look at the key for the periodic table though, because some of them put the relative atomic mass at the top and others at the bottom, and you need to make sure you're picking the correct one. After the relative atomic mass, you can calculate what is known as the relative formula mass. And the relative formula mass is very similar, but the word formula tells you that it's going to have to do with the chemical formula. What this means is that we're going to use something like, for example, CO2 or carbon dioxide, and we know that there's 1 carbon atom in it, and that there are 2 oxygen atoms in it. If we wanted to find the relative formula mass of this, we would need to take 1 times the mass of carbon, which is 12, and add it to 2 times the mass of oxygen, which is 16. In total, this would give us 44 atomic mass units as the relative formula mass for this compound. There's another type of formula that we might need to determine, and that is the empirical formula. This is the simplest ratio between the atoms of a molecule. In order to determine this, you need to use the largest common factor with your formula. Let's take the example of glucose, C6H12O6. In this case, the largest common factor is 6, so we'll divide each of the numbers by 6. 6 divided by 6 is 1, 12 divided by 6 is 2, and 6 divided by 6 is 1. Now, as lazy chemists, we'll ignore these ones, so the formula for glucose is CH2O. This is the simplest ratio between the elements in the compound, and it lets you know in what proportions they're combined. On a different note, though still related, we're going to talk about pure versus impure. In chemistry, the word pure means that there is only one element or compound present. So that's some bad news for those of you who've bought pure orange juice, because as we know it contains some water molecules, some sugars, some flavors, etc. So chemically speaking, they were lying to you and it's not pure. That doesn't necessarily mean there's anything wrong with it, it just means they haven't studied their chemistry. In order to determine if a substance is pure or not pure, one of the techniques we often use is the melting point. If you take a substance and you increase its temperature, you will approach its melting point. If the substance is pure, at the melting point you'll have this flat plateau, and then your temperature will start to rise again. From physics, we know that what's happening here is that the bonds are breaking, and that energy is the specific latent heat. That's the energy to break those bonds. That black line is for a pure substance. If the substance is impure, however, you'll find that as you approach the melting point, you'll get a variation in your temperature, and that you'll have a wide range of time where the substance is melting, and a wide range of temperature. All of those temperatures, however, will be below the expected pure temperature. If we were dealing with pure water, the temperature would be 0, but if you're dealing with impure water, then the temperature will be below that. And that will depend entirely on what molecules are present or what impurities are present. Now that you know something is pure or impure, if it's impure, you might need to separate it. And there's a bunch of different techniques that we need to know in order to be able to do that. In filtration, you are separating an insoluble substance from its solution. Insoluble means that it cannot dissolve in that solution. Your setup is going to involve a funnel, some filter paper, and then a container to catch the substance that you've filtered. You'll pour your sample into the top, and you'll have a residue of insoluble solid, and then you'll have some liquid that makes it through the filter, and that is your filtrate. It's important to note that anything soluble will make its way through the tiny holes in the filter paper and end up in the filtrate. If you need to separate that out, you'll need another separating technique. Another technique for separating something is distillation, and this relies on different boiling points to separate the mixtures. Your setup will involve some sort of heat source, and then a container with your substances. At the top of the container, you'll be connected to a condenser. If you imagine a mixture of two substances, the red substance has a higher boiling point than the green substance, and they're both heated at the same time. Well, the green substance will boil first and reach the condenser. When it does, it will cool and turn back into a liquid, and then come out of the other side of the condenser to be collected. In some cases, you need to have something more complex. You may be separating several different fractions from the solution, or you may have some solutions with very close boiling points. In this case, you need to add some distance and some opportunities for something that's boiled a little bit before its time to condense back again, and so you'll add a fractionating column. Before your condenser. In this case, all of the green substance would have to have passed through before the fractionating column will be able to heat up to the point that the boiling point of the red substance is reached. And so it separates the two compounds out with a little bit more distance because it takes time for that heating to take place. Another technique that we have is chromatography. And in chromatography, you have two phases. You have the stationary phase, and you have the mobile phase. The attraction for these two phases for the compound that you're trying to separate allows the stationary phase to slightly hold on to it, and the mobile phase to move through and pull. And depending on how your substance is attracted to either the stationary or the mobile phases, it will separate out more or less. For paper chromatography, you begin with a sheet of paper and you trace a pencil line. This means that you're not going to have any compounds that are going to mix from if you traced it in ink, for example, into the substance that you're trying to separate. Then you would place your sample, as well as any other samples that you wanted to compare, onto the paper. And then you'd place the whole setup in a beaker or other container, and you'd need to make sure that in there, the solvent or the mobile phase is below the pencil line that you'd traced, so there's no mixing that happens. The mobile phase would then move up the page, pulling the substances along with it. A very similar thing happens in gas chromatography, but instead we have a heat source, and so your sample will pass through the heat source and become a gas, and then it will travel down a long tube, and at the end it will come out in front of a detector. The detector will register the output from the tube, and you'll get a graph that looks something like this. This would show that in fact 2 substances came out as a function of the time that it took for them to come through the tube. This also allows you, if you're studying triple and higher, to look at the area under the curve, and then that will tell you how much of the substance there was. You can use chromatography to verify the purity and to compare different compounds. We'll use an example. In this example, we have a green dye, and we want to see if any of the compounds in this dye are comparable to either the yellow dye or the blue dye. And so we would allow the compound to go through, and then we would see how the various different parts of the dye moved. You could then do a qualitative comparison by looking across and seeing that the 2 yellow spots match, but the 2 blue spots don't match. And so the yellow dyes are likely the same, but the blue dyes are not the same. However, we can also get a quantitative value for this, known as the RF value or retention factor. And that's the distance that the spot traveled divided by the distance to the solvent. Now, when we say solvent front, we mean this sort of line at the top of the page where it got wet until, or where the solvent was able to kind of travel up the page and it reached that point. So that's kind of the maximum. This means that the value is always from 0 to 1, and if you don't get a value from 0 to 1, then you know that your correction is to swap these 2 round so that you do get that value between 0 to 1. Next, we're going to look at one of the most beautiful things in chemistry, the periodic table. It was developed by a scientist named Dmitry Mendeleev, and he did 3 interesting things. He wasn't the first to do something similar, but he was the first to sort of put them all together. He grouped elements by their atomic mass, which is similar to the relative formula mass we have today. He also grouped them by their chemical properties, so how they reacted, and by their physical properties, or how dense they were, or what their boiling points were, etc. And what he found when he looked at these 3 things together is he found a pattern. And the pattern repeated every 7 elements. Nowadays, we know that it's every 8 elements, but because elements at that time were discovered by reacting them with other things, and the noble gases don't react, the noble gases had not yet been discovered. What Dmitry Mendeleev did next was to leave blank spaces where the pattern didn't match. So, for example, if we know that every 7 elements there's going to be a reactive nonmetal, and we're not at the reactive nonmetal yet, then he would leave a gap for a new element to be added to his table when it's discovered. One of these elements was gallium. It was found that Mendeleev had actually done a very good job of predicting the properties of the element, even though it had not yet been discovered when he'd made his predictions. Looking at the periodic table, you can tell where the metals and nonmetals are based on the position of an element in the table. But you can also tell the difference between them by their properties. Metals are generally shiny. They generally have a high melting and boiling point. They're also ductile, which means they can be stretched into wires, and malleable, which means that they can be bent. You'll find that they are also good conductors of both heat and electricity. In contrast, nonmetals are usually dull in appearance, They usually have lower melting and boiling points. You are not able to bend or stretch them, making them brittle. And they are insulators, so they are not very good at conducting current, electricity, or heat. The properties that metals have are because of the structure that the metal has. If you picture the nucleus of a bunch of different metal atoms, you'd see that you've got sort of the positive nuclei that would be arranged in regular rows, and then around each of these, if we just draw the outer shell, you'd have space for electrons. The electrons of a normal atom would be stuck in their outer shell, but with a metal, we say that they are delocalized. And this means that the electrons are free to sort of flow in between all these different atoms. And what that means is that if you apply a force to one side, well, all the atoms just shift over and the electrons shift over, and then the bonds are still there. And that's what allows them to be malleable or ductile. And if you add a potential difference across this, then you'll get current electricity flowing through it because the electrons are able to move through the substance. The next thing we'll discuss is the concept of forming an ion. And what this means is that you're either losing or gaining electrons in order to become charged, either positively or negatively, and you'll do this to become stable, i.e. to have the same electronic configuration as a noble gas. And this is what happens in the process of forming ionic compounds. We'll look at a classic ionic compound, sodium chloride. The sodium atom is in the third row of the periodic table. The electronic configuration tells us that there are going to be 3 shells, 1 for each row, and that the first 2 will be full, so therefore 2 in the first shell and 8 electrons in the second shell. In the third shell, sodium has 1 final electron, making it relatively unstable. If possible, it will lose that electron and then become charged positively by 1 and have sort of an empty invisible outer shell and drop back down to look like the nearest noble gas with the full shell of 8. Chlorine is very similar. Also in the third row, it has 2 electrons in its first shell, 8 electrons in its second shell. In chlorine's third shell, however, it has 7, meaning that it needs just 1 more electron, and it could get that from sodium. If it did, then chlorine would become charged negatively by 1, and then you have a positive charge and a negative charge, and so opposite charges attract and the compound is held together. The other type of compound is the covalent compound or the simple molecule. In this case, you are dealing with 2 or more nonmetals, and you're dealing with shared electrons. When we're drawing this type of compound, we only worry about drawing the outer shells, and let's use the example of carbon dioxide. We'll draw overlapping circles to show areas where the shared electrons would be, and then we'll go about placing them. Let's begin with carbon. Carbon has 4 electrons and needs 4 more electrons. It's going to share its 4 electrons with the 2 oxygen atoms to either side. A sharing partnership is an equal partnership, so oxygen is going to put in 2 electrons of its own. This means that for carbon, there are 1, 2, 3, 4, 5, 6, 7, 8 electrons. It has a full outer shell. And the same is true for oxygen. It has the 4 electrons that are not involved in a bond, and then its original 2, plus 2 more, giving it 8 total. This means that it's in a stable configuration. These covalent compounds can also form giant covalent structures where you get a repeating covalent structure that is very stable and often useful. One of the best compounds to form these structures is carbon, and it will form what are known as allotropes, or different forms. One of the most expensive of these is diamond. You need to know that diamond is non-conductive and that it is very strong, which you probably already knew. The reason for this is that it only has covalent bonds. Each carbon atom is bonded to 4 more carbon atoms in order to form a structure, and then other structures similar to this are bonded to the first structure in order to form a giant compound. Another allotrope of carbon is graphene. Graphene is formed of 6 carbon rings that are joined to each other and in this ring there are delocalized electrons. And the reason for this is that each carbon atom is bonded to 3 other carbons, and therefore that leaves 1 electron free in order to be delocalized, which means that graphene will conduct electricity, and that is what allows it to be used, for example, in touch screens. A similarly conductive material is the buckyball, which is a C60 configuration, and it looks a little bit like a football in that the carbon rings are arranged to form a sphere, and this has been used in a number of different contexts, including in the medical context. Whenever you put substances together, the whole joined up substance will have certain properties that belong to it, and these are the bulk properties which will depend on the lattice or crystal structure. We know that metallic lattices are conductive and malleable, but ionic compounds are often not. Some covalent compounds can be soft, such as wax, or they can also be brittle. Such as iodine. The final place where the bonds will affect is in changes of state. If you are changing state, then that means you are breaking bonds. Some bonds from liquid to solid, or rather solid into a liquid, and then all bonds between liquid and gas. So certain substances, for example oxygen, wax, other compounds like water, they will have low boiling and melting points, because they have weak intermolecular forces holding them together. Metals, on the other hand, would have a much higher melting or boiling point because the metal would be much stronger in those metallic bonds that hold it together. So when you put all of this information together, you're in a space that you should be ready to answer some very interesting chemistry questions. Speaking of those questions, there is a worksheet in the description for you, and the answers to that will be up next week. Until then, happy sciencing.